Today we are starting on our final lesson of Chapter 16. Until now, we've worked with discrete random variables. And with these discrete random variables, each outcome had its own specific probability, and we were able to calculate these. Now we are moving from discrete to what's considered a continuous random variable. And if you remember from the very first lesson when we defined continuous random variable, they can take on any value. They can be decimals, they can be fractions, and so because they can take on any value, we are not able to assign a single probability to each value. So now, because x can take on any value, which means it has any mean and standard deviation, we need to take all of these different variables that exist and standardize them so that all of our data is the same so that we can now calculate probabilities. And we talked about standardizing scores back in Chapter 16. If you remember back in Chapter 16, we learned about these things called z-scores. And we're going to be using z-scores again in this particular part of Chapter 16 because z-scores display continuous variables. So we're going to take a look at some instructions on how to break down these problems. So when you have continuous variables, we have a 7-step process. The first thing you need to do is simply define your variables. In other words, give a variable for each item that's being discussed in the problem. Then, once you've done that, step 2, you need to look at what the problem is asking you to calculate and write an appropriate equation for the problem. It might be using addition. It might be using multiplication. It might be using subtraction. Once you've written your equation, then step 3 is to calculate the expected value for the combined variables. So this was an equation that we saw back in lesson 3. If you have the expected value of two variables being either added or subtracted, you simply add or subtract their separate expected values. After you have the new expected value for your combined variable, then you have to calculate the variance of your combined variable. This again was one of the equations that we saw back in the previous lesson. If you have two variables that are either being added or subtracted and you want to find their variance, this was the one that we had to remember. Variance is only addition. So you're always going to add the two variances together. Once you have the variance, the other thing that we need is to calculate the standard deviation. And as you already know, you simply square root variance to calculate standard deviation. Once you have your expected value, which remember is another name for the word mean, and your standard deviation, you can find your z-scores using the z-score formula that we learned way back in Chapter 6. And that's this formula right here. To calculate your z-score, you take your x value minus your mean divided by your standard deviation. Then once you have your z-score, you draw your little normal curve, either shade to the right or shade to the left, and then use your blue sheet or our calculator shortcuts to find the appropriate answer. And so what we're going to do is we're going to go through 3 separate examples working through these steps. The first couple of examples I'm going to break down very step by step for you, but then after that we're going to look at 2 examples that are more like what you're going to see on your homework, where you need to know how to put those examples, all those steps together. All right, so let's look at the first example. A company manufactures small stereo systems. At the end of the production line, stereos are packaged and prepared for shipping. The company says that the time for the packing stage can be described with a normal model with a mean of 9 minutes and a standard deviation of 1.5 minutes. The boxing stage can also be modeled as normal with a mean of 6 minutes and a standard deviation of 1 minute. So we have lots of stuff going on here. We're going to answer the question, what is the probability that packing 2 consecutive stereo systems takes over 20 minutes? So we need to define our variables here. So we're talking about 2 stereo systems and we're talking about packing two stereo systems. So I'm just going to let the letter P be packing. But I'm going to use P sub 1 for packing box 1. And I'm going to let P sub 2 be packing box 2. Now, we need to write an equation. Well, we want to know what's the probability that packing 2 of them takes over 20 minutes. So we're combining the packing times together. So we're going to take the packing time for the first one and add it to the packing time for the second one. Now, if we look back up on our word problem just to make sure we have all the right data, our packing stage has a mean of 9 and a standard deviation of 1.5. Our boxing stage, which we're not using yet, has a mean of 6 and a standard deviation of 1. Well, the one thing that we need for both of these is our variance. So, and I'm color coding so that it makes it easier to keep track of, our variance for packing. If you remember, to find variance, we take standard deviation and we square it. So 1.5 squared is 2.25. Our variance for, I'm just going to use B for boxing, same thing. The standard deviation is 1. We're going to square it and we get 1. So we have all of our necessary data to keep going. So I've done step 1, I defined my variables. I've done step 2, I've written my equation. Now we're going to go on to step 3, which is finding the expected value. So to find the expected value, we're trying to find the expected value of packing 1 plus packing 2. Well, according to our equation on step 3, all we have to do is take the expected value of packing 1 and add to it the expected value of packing 2. Well, what's the expected value or the mean for the packing stage? If you look back in your paragraph, it said the packing stage can be described with a normal model with a mean of 9 minutes. So packing the first box takes an average of 9 minutes, and packing the second box takes an average of 9 minutes, for a total mean or expected value of 18 minutes. Now we have to do step 4, which is finding the variance. So we need to find the variance of packing 1 plus packing 2. Variance is the one that is always addition. So the variance of P1 plus the variance of P2. So if you go back to, again, our previous slide, when we did the variance for P, we ended up with 2.25. So 2.25 plus 2.25 is a total of 4.5 minutes. Step 5, find the standard deviation. To find the standard deviation of P1 plus P2, we need to square root the variance of 4.5, round to 1 decimal, and you get 2.1 minutes. So now we have the mean, 18 minutes, and the standard deviation, 2.1 minutes, for our new combined variable. So now we're going to go back and focus on what was that question that was originally asked of us. The original problem asked, what is the probability that packing 2 consecutive stereo systems takes over 20 minutes? So we need to find our z-score for over 20 minutes. Our z-score formula starts off with the x value. Well, our x value that we're focused on here is 20 minutes minus the mean. Well, what was the mean that we found in step 3? That was 18 minutes divided by the standard deviation that we found in step 5, which was 2.1 minutes. And so 20 take away 18 is 2, and 2 divided by 2.1 is, and if you remember, z-scores are always 2 decimals, comes out to be 0.95. So there's our z-score. So now that we have our z-score, we can draw our little model. So if you remember back in chapter 6, we draw our curve. 0 was always in the middle. So positive 0.95 would be on the right. Which side are we shading? Well, the key word was over 20 minutes. So we are shading the right side. So if we go to our blue sheet and we go to our positive side and we go down to 0.9, remember that's 0.95, we get 0.8289. Now, you got to think back to what we did in chapter 6. If you remember, the blue sheet only shades to the left. And so if we need to shade to the right, whatever answer we get from the blue sheet, we need to take 1 minus that answer to figure out the answer that we want. And so if we take 1 minus 0.8289, we get 0.1711. And that is the probability that it will take over 20 minutes to pack 2 systems. And so when it says on H, these are like thinking questions, interpret your results, all we can simply say is it takes approximately a 17% chance it will take over 20 minutes to pack 2 boxes. So there's only a 17% chance that it will take over 20 minutes. So that means that the chances of it taking under 20 minutes are a lot better. So this was one example. We're going to do another one where we walk through the steps. We're going to keep using our stereo system. I'm just changing the question. I now want to know what percent of the stereo systems take longer to pack than to box. So now we're combining our 2 variables together. Well, first we need to define our variables. I'm going to continue to let P be packing, and I'm going to continue to let B be the boxing. The equation part here is a little bit different. We want packing to take longer than boxing. So that means that packing is going to be the bigger number. And when we're trying to show something is larger than the other one, the operation we usually use is subtraction. So the packing time should be longer than the boxing. So we're going to take packing minus boxing to figure out the difference in their times. So the first thing we need to do, now that we have our equation, is find the expected value of packing minus boxing. Well, the expected value equation says we simply take the expected value of packing minus the expected value of boxing. If you go all the way back to our first example where it listed all of our information, the mean, which is the same thing as expected value, the mean packing time was 9 minutes, and the mean boxing time was 6 minutes. And so the mean of their differences is 3 minutes. So next slide, continuing up, we need to find the variance. So we need to find the variance of packing minus boxing. But variance is always addition. So I'm thinking ahead here, sorry. So the variance of packing has to be added to the variance of boxing. It's always addition. So if you go back again to our original, we already knew that the packing variance was 2.25, The boxing variance we found was 1 for a total of 3.25 minutes. Now we need our standard deviation of packing minus boxing, which means we need to square root the variance. So the square root of 3.25 rounded to 1 decimal is 1.8 minutes. So this was steps 1 through 5 of our process. Now step 6 is when we go back and we find the z-score and we focus on the original problem. What percent of the stereo systems take longer to pack than to box? Well, if you remember, we did packing minus boxing. And if packing has to take longer than boxing, that means that packing is the bigger number. And when you take a bigger number minus a smaller number, your answer will always come out to be positive. So what we're trying to solve here is that packing minus boxing has to be bigger than 0. Because packing has to take longer than boxing. So bigger minus smaller is always positive. So our z-score. I had to do this before I could find my z-score because I had to know what my x value is. My x value is 0. Then we are subtracting our mean. And if you look back on part C, our mean was 3. Divided by our standard deviation, part E, that was 1.8. So we have negative 3 over 1.8, which comes out to be, with 2 decimals, because it's a z-score, negative 1.67. So now we need to find the probability. Well, there's our picture. We know 0's in the middle. We know negative 1.67 is somewhere over here. And so we are trying to find, if you look back up at the top, we needed greater than. So greater than means that we are shading again to the right. And so if we go to our negative side this time, and we go down to negative 1.67, we get 0.0475. But again, from our blue sheet, they always shade left. We need right. So we're going to take 1 minus 0.0475. And if you take 1 minus 0.0475, you get 0.9525. So that is our probability that packing will take longer than boxing. And so the question is, what percent of stereo systems take longer? We could simply interpret our results with approximately 95.25% of stereos take longer to pack than box. And that's the end of that example. Now, so far, we've walked through each one of these very much step by step by step. So we're going to do we're going to step it up a little bit so that it looks more like the questions that you're going to see on. So let's look at example 14. Bicycles arrive at a bike shop in boxes. Before they can be sold, they must be unpacked, assembled, and tuned. Things like lubricating, adjusting, etc. Based on past experience, the shop manager makes the following assumptions about how long this may take. First of all, the times for each setup phase are independent. The times for each phase follow a normal model, and the means and the standard deviations in this table are in minutes. So we need to figure out what are the mean and standard deviation for the total bicycle setup. Well, the total setup would be unpacking, assembling, and tuning all together. So let's use some common sense variables. Let's say that unpacking is U, assembling is A, and tuning is T. Well, the total bicycle setup time would simply be adding all three of those together. Sounds pretty simple. So there's our equation. We need to find the mean, which is another name for expected value, of U plus A plus T. So that simply means that we need to take the expected value of U plus the expected value of A plus the expected value of T. Well, U is 3.5, A is 21.8, and T is 12.3 for a total assembly time of 37.6 minutes. We now need to find the variance of U plus A plus T. Well, the problem is we don't have variance yet. So I'm going to add a column to this table here for variance. We already know that to find variance, we have to square standard deviation. Well, 0.7 squared is 0.49. 2.4 squared is 5.76. And 2.7 squared is 7. That's supposed to be a 29. So let's come back over here. Variance is always addition. So we're going to take the variance of U plus the variance of A plus the variance of T, which would be 0.49 plus 5.76 plus 7.29 for a total of 13.54 minutes. But we also need to find the standard deviation of U plus A plus T. So we need to square root 13.54. And if we square root 13.54, we get 3.7 minutes. That is your variance, and this was your mean. Those are the two that we need. So this is more what you're going to be doing on your homework. It's not quite as broken down. You still think through the steps, but it's not part A is this, part B is this, part C is that. It's just a little more straightforward. So let's look at the next slide. As the question. A customer decides to buy a bike, like one of the display models, but wants a different color. The shop has one, but still in the box. The manager says they can have it ready in half an hour. Do you think the bike will be set up and ready to go as promised? So if it's going to be ready in half an hour, that means that the total unpacking, assembling, and tuning time is going to be less than half an hour is 30 minutes. The less than is important because it tells us how to shade. Because if it's more than 30 minutes, it's not what the manager promised. So this is the part where we have to find our z-score. So half an hour was 30 minutes. If you look back on the previous part of your notes, the mean was 37.6 divided by the standard deviation, which was 3.7. 30, take away 37.6, divided by 3.7, 2 decimals, is negative 2.05. So there's our z-score. Our picture, zero's in the middle. Negative 2.05 is somewhere way over here. And there's our line. We already set up here, has to be less than 30 minutes, which means we are shading to the left. And if you go to your blue sheet, you go to negative 2.0, and then you go over to 5, you get 0.0202. And so what does that mean? So that simply means that there is approximately a 2.02% chance the bike will be ready in less than 30 minutes. So the chances of it being ready on time are pretty slim. Let's look at one final example. The bicycle shop that we were just talking about, in example 14, will be offering 2 specially priced children's models at a sidewalk sale. The basic model will sell for $120 and the deluxe model for $150. Past experience indicates that sales of the basic model will have a mean of 5.4 bikes with a standard deviation of 1.2. The sales of the deluxe model will have a mean of 3.2 bikes with a standard deviation of 0.8 bikes. The cost of setting up the sidewalk sale is $200. So let's underline some things. So let's start with blue for basic. So basic, they sell for $120, and basic have a mean of 5.4 and a standard deviation of 1.2. Let's use red for deluxe. Deluxe sell for $150. They have a mean of 3.2 and a standard deviation of 0.8. But then there's this other random number. The cost of setting up the sidewalk sale is $200. That's automatic lost money. So this one's a little trickier. It says define your random variables and then use them to express the bicycle shop's net income. In other words, what's the money that the bicycle shop will actually make? Well, let's start by defining some variables. Let's be smart about this. Let's just use B for basic and D for deluxe. Now, the money that the shop makes is based on how much each bike costs. So, each deluxe bike, they're making $120 on. So, I'm going to write that as $120 times your basics. Your deluxe, they make $150 off of each. So that's $150 times your deluxe. Now, the money they're making, those two get combined. The problem is they are losing a little bit of money for setting up the sidewalk sale. They're losing $200. So we just need to subtract $200 off of that cost. So there's our formula. So income, they make $120 per basic bike, $150 per deluxe, but they're losing $200 for setting up the sale. So now we need to find the mean, or the expected value. So the expected value of 120B plus 150D minus 200. So, got to dig deep into the last lesson. Anytime there was a number in front of your variables, you simply took 120 times that expected value plus 150 times that expected value. Now, anytime there was just a number added or subtracted at the end, it only affected expected value. So we simply need to subtract off the 200 at the end. So we're going to take 120 times, if we go back up to our underlined stuff, basic has a mean of 5.4 plus 150 times. Deluxe had a mean of 3.2, but we need to subtract 200. Now you can put all of that in your calculator at one time. 120 times 5.4 plus 150 times 3.2 minus 200, and you end up with a mean of $928. So their average income from the sale is $928. Now they want us to find the standard deviation. Well, in order to find standard deviation, we first need to find the variance of 120B plus 150D minus 200. So again, if you remember from the previous lesson, Variance, we took the number in front and we had to square it times the variance of B. Variance is always addition. Take the number in front, square it times the variance of D. But the other thing, if you remember, variance is not affected by constants. It's not affected by the 200. So the 200 basically doesn't exist. So we're going to take 120 squared times, well, we need to figure out the variance of B. If we go back over to our basic bikes had a standard deviation of 1.2. So if we take 1.2 and we square it, we get 1.44. Our deluxe bikes had a variance of 0.8. I'm sorry, standard deviation of 0.8. When we square it, we get a variance of 0.64. So now we can fill those in. So the variance of basic was 1.44 plus 150 squared times 0.64. If you type all of that in the calculator, you will get a rather large number. I get $35,136. But the only reason we found that was to find the standard deviation of 120B plus 150D minus 200. So we need to square root that 35,136. And I got a standard deviation of $187.45. And I rounded to 2 decimals because it's money. Final question. What's the probability that the total sales will be greater than 1,200? So, on to the z-score. Our x value is 1,200. Our mean from our previous slide is 928. Our standard deviation that we just found was 187.45. 1,200 minus 928 divided by 187.45 comes out to be a positive 1.45. Zeros in the middle. 1.45 is over here on the right. We need greater than, which means we need shade to the right. So if we go to our blue sheet and we look up 1.45, we get 0.9265. But this is a shading to the right problem, so we need to take 1 minus 0.9265, which comes out to be 0.0735. So, what are the chances of sales being greater than 1,200? There's only a 7.35% chance sales will be greater than $1,200. And that's the end of chapter 16.